Hello everybody, welcome back. Today we're going to be taking a look at some gamma functions. Um, so the gamma function is really just an extension of the factorial that we all know and love. Um, let's read the problem. Show that the binomial coefficient p choose n can be written in terms of gamma functions. So here's our two definitions for the gamma function that we have here. Um, the gamma function of q is either this integral here, or it is um, it's the factorial of 1 less than q. So um, the binomial coefficient, if you remember, there's a couple different ways that it pops up. Um, what it got its name from though is if you have a binomial like x plus 1 and then you raise it to a certain power like 3, then the way you write that out is x cubed plus 3x squared plus 3x plus 1 once you do all the foiling out. It's a little more than foiling because you're cubing, but see how there's a 1, a 3, and a 1? The 1 is implied here. Um, those are your binomial coefficients. So um, your p is what you're taking it to the what you're taking it to the power of, and then your n is which one you're interested in. So like this is n equals 1, that's n equals 2, that's n equals 3, that's n equals 4. Actually, yeah, that's n equals 0, 1, 2, and 3. My bad. So yeah, that's the binomial coefficient. Usually the way that you figure it out, the typical definition for that, Pn is equal to P times P minus 1, P minus 2, dot, 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 all the way down to P minus N plus 1. And this is all over N factorial. So what I'm going to do for this problem is I'm going to multiply the top and the bottom by a interesting form of 1. This is something we do all the time to simplify our solutions. So our interesting form of 1 this time is going to be p minus n factorial over p minus n factorial. So what this does is this completes the sequence for the top. So we were going from p all the way to p minus n plus 1. But now we're multiplying it by p minus n minus 1, all the way down to 1. So this completes the sequence up the top. So that's just going to be p factorial. And then we're going to have n factorial times p minus n factorial. And this is actually a form that you'll often see it written in. When I originally learned the binomial coefficient formula, this is the way I learned it. So, and then all we have to do here, since we've written this in terms of factorials, it's not too bad to turn it into gamma functions. So, the gamma function of q is the factorial of q minus 1. So the factorial of p is the gamma function of p plus 1. P plus 1. And then same down here, the gamma, or the factorial of n is the gamma function of n plus 1. And the gamma function of, or the factorial of p minus n is the gamma function of p minus n plus 1. That's not a bad problem. This is a pretty simple problem. Anything you can write as factorials, you can write as gamma functions. There's a lot of things you can write as gamma functions that you can't write as factorials because factorials are not typically thought of as being for non-integer values. But there's nothing stopping, since the gamma function is defined primarily by this integral here, there's no reason any of these can't be any number that you want. It's just a matter of some peculiarities with negative numbers. So yeah, so since we're defining the binomial coefficient by gamma functions now, we can use it for things that are not integer values. And you all know I love visualizing things, so let's take a look at that. So here we have our Desmos is nice, and they let you put in factorials for non-integer values, and they don't mind. It's a lot easier than trying to figure out where the gamma function key is on this. So yeah. Well, let's take a look here. So in this scenario, our x-axis is our p, and our n is defined by here. So in terms of like permutations and combinations, we're taking x choose our constant n. So you can get some really funky looking things if you drag this along here. So let's see. I'll go ahead and well, yeah. So one thing to note is that for integers, this behaves a lot differently than for non-integer values. So for any negative number, it's 0 everywhere. There's no way to choose a negative amount of things. However, for every situation, there's exactly one way to choose 0 things, and that's to choose 0 things. Then for every x things you have, there's always x ways to choose 1, and that is to just choose 1. Then it gets a little more complicated here. You can see that it crosses 0 every integer here, which is a useful property. That means that there's no ways to choose, like for example, there's no way to choose 4, or there's no way to choose 6 things out of 4, or there's no way to choose 5 things out of 4. However, if you look at where 6 is at 1. There is one way to choose 6 things out of 6, and that's to choose all of them. So as you can see, it gets steeper and steeper as you go along. That just means that when you're choosing more things out of more things, there's more ways to do it. Let's take a look at the animation though, because I enjoy this. Actually, yeah, so this is counting up from -10. So you can see it's getting pushed further to the right, and it's also getting steeper. Let's look at this animation again, but with non-integer values for n. I'm not 100% sure what's going on with that, but I think there's something, if not insightful, at least humorous about the way that this works when you have non-integer n, which is probably why in any practical application, at least that I know of, you definitely use integer n's for the binomial coefficient. Thank you for watching.